Newton's third law of motion is weird. For every action, there is an equal and opposite reaction. In this video, we'll explore this law logically and see how Newton experimentally proved it using just two pendulums. We'll also look at a modern, simpler way to demonstrate the third law. According to Newton, when you apply force to an object, the object applies an equal force back to you. This seems strange. Why should something push back when you apply force to it? Yet, this is Newton's third law. Though it may seem odd, it is true. If you ignore this reaction force and try to predict motion, you will get completely inaccurate results. Let's look at a few everyday examples to better understand Newton's third law. When you lean against a wall and push it with your back, assuming the floor is frictionless, you're applying force to the wall. But what happens? You move away from the wall because of the reaction force produced by the wall. We're all familiar with the boat example. Here, you're pushing the boat to the left. According to the third law, the boat gives a reaction force to you, pushing you to the right. This is why you move. Notice that the boat moves backwards because of the force you applied. Now, you might be wondering, when you hit a ball with a bat, you're obviously applying a good amount of force to the ball. Does this mean the ball applies an equal force back to you? Yes, the ball transmits an equal force to you. So why don't you move backward? This is due to the friction between your feet and the ground. To understand this better, let's imagine hitting the ball while standing on ice, where there's almost no friction. In this case, when you hit the ball, you'll slide backward. How did Newton prove such an important law experimentally? He used a simple two-pendulum setup. Newton observed the velocity of the balls before and after their collision. Let's rewind the scene. The first ball reaches its maximum velocity just before the collision. But after the collision, both balls' velocities change. Newton knew that if the forces transferred during the collision were equal and opposite, the ball's velocities before and after the collision had to obey certain conditions. This condition can easily be derived from the third law, which we'll explore later in the video. At the time, there were no instruments to measure velocity, so Newton relied on the fact that a pendulum's velocity at its lowest point is proportional to the cord length. However, there was a big challenge: air resistance, which significantly affected his velocity calculations. To overcome this, Newton used a tricky method described in his book Principia Mathematica. By using this method, he could accurately predict the velocity of the ball at the bottom, even accounting for the air resistance. Here's how he did it. Newton released the first pendulum after withdrawing the second one. He marked the return point of the pendulum as V, and the distance, RV, corresponded to the total air resistance. The distance, ST, was 1/4 of RV. The trick was, if you release the pendulum from point S, due to air resistance, the speed at the bottom would be the same as if the pendulum had been released from point T in a vacuum. In short, the speed is proportional to chord TA, not SA. Using this clever reasoning, Newton proved that the velocities of the balls before and after collisions perfectly follow this equation. In short, the force ball A given to B is the same as the force ball B given to A. Please note, the complete mathematical analysis of Newton's pendulum experiment is beyond the scope of this video. In today's world, we have an easier way to prove Newton's third law, with an experiment known as Newton's nightmare. Let's see how it works.
Aluminum tube and a permanent magnet. There is no force of attraction between these two. But when I drop the magnet inside the tube, did you see that? The permanent magnet moves extremely slow. the permanent magnet slows down because the eddy current induced in the aluminum tube opposes its motion. Anyway, now using a weighing machine, let's prove Newton's third law logically. You can see here the weight of the aluminum tube plus the permanent magnet is 170 grams. When I remove the magnet, obviously the weight decreases. But when I drop the magnet inside the tube, remember the magnet is not touching the tube. The weight is back to almost 170. How did this happen? Even though the magnet is not touching the tube, how did the weight come back to the same as the previous? The answer lies in Newton's third law of motion.
Let's explore this in more detail using animation. Here are the magnetic field lines around the magnet. The moving magnetic field first induces eddy currents in the aluminum tube. These eddy currents generate another magnetic field that opposes the magnet's motion. This means, according to the third law, the permanent magnet should also give a force on the aluminum tube in the opposite direction. This is why the weight measured increases. After a while, the magnetic repulsive force equals the magnet's weight, and the magnet moves at a constant speed. At this point, if you measure the weight, it will equal the combined weight of the aluminum tube and the magnet, proving Newton's third law of motion. Now, let's look at an interesting derivation of Newton's third law. Consider two balls of equal mass, one moving and the other at rest. If the moving ball hits the resting ball in a perfectly elastic collision, what would you expect? You might think the moving ball would reverse direction and continue at the same speed, which makes sense according to the conservation of energy. But this won't happen due to Newton's second law. What actually happens is that the first ball comes to a complete stop, and the second ball moves with the speed of the first ball. Let's analyze this in ultra-slow motion. Assume the collision happens in delta t seconds. During this brief time, the two balls exchange forces. According to the third law, the force the first ball applies to the second is equal in magnitude to the force the second ball applies to the first. We know that force is the change in momentum divided by the time over which it occurs. Rearranging this, the third law can be expressed as momentum before the collision equals momentum after the collision, assuming no external forces act on the objects. This is the principle of conservation of momentum. When we apply this principle, along with conservation of energy to these two balls, the first ball comes to rest, and the second ball moves with the same speed as the first. Conservation of momentum is a user-friendly form of Newton's third law, and it's widely applicable. What would happen if Newton's third law didn't exist? The answer is simple. The world wouldn't be as we know it today. Rockets wouldn't fly, and we wouldn't even be able to walk. That's right. You can walk because of Newton's third law. You push the Earth, and the Earth pushes you back. This reaction force propels you forward. The effect of your push on the Earth is negligible because the Earth's mass is so large.
Now the big question, how did Newton come up with such a law? How did he understand the reaction force as an equal magnitude to the action force? The answer, pure imagination and unbelievable intuition. Before you leave this video, please subscribe to this channel. Also, please share this video with your friends and family. Take care. Bye-bye.